The moon is the only place beyond this planet where anybody has stood. It is also the thing most people have looked at more often than any other object in the sky, and mostly without thinking about it. It is up there. It changes shape. It goes away and comes back. Tonight we are going to spend the whole time on it. 14 things. All of them measured rather than guessed, starting with what you can see from a window and ending with how long a footprint lasts up there. Where the measurements disagree, or where the honest answer is that we are not certain, I will say so. There is no rush in any of this. You do not have to follow every number. If you are here to fall asleep, that is a perfectly good way to listen. There is no dark side. The phrase is very common, and it is wrong. There is a far side of the moon. There is no permanently dark side. Every part of the moon gets sunlight. The moon turns on its axis, slowly, and as it turns, the line between day and night sweeps all the way around it, just as it does here. A lunar day lasts about 29.5 of our days, measured from one sunrise to the next. So a spot on the surface gets roughly 14 days of sunlight, then roughly 14 days of night. The side we never see gets exactly as much sun as the side we do. When we are looking at a full moon, the far side is in complete darkness. When there is a new moon and we can see nothing at all, the far side is in full daylight. The confusion comes from the word dark being used to mean unknown, which it was entirely until 1959, when a Soviet probe called Luna 3 went around the back and sent home 29 photographs. They were poor photographs by any standard. They were also the first time anyone had seen almost half of a world that had been in the sky the whole time. The face that never turns away. The moon keeps one face towards us. This is not a coincidence, and it is not unusual. It is called tidal locking, and most large moons in the solar system do the same thing around their planets. It happens because the Earth pulls slightly harder on the near side of the moon than on the far side. Over a very long time, that difference acted as a brake on the moon's spin, until the spin settled at exactly the rate that keeps one hemisphere pointed inward. The moon does rotate. It rotates once per orbit, which is why the same face stays towards us, but we do not see exactly half of it. The moon's orbit is slightly oval, so it speeds up and slows down as it goes round, while its rotation stays even. It also tilts a little. The result is a slow rocking, back and forth and up and down, called libration. Over the course of a month, that rocking lets us peek a little way around each edge. Add it all up, and about 59% of the surface is visible from Earth at one time or another. The remaining 41% had never been seen by anyone until a camera was sent around the back. 400 and 400. The Sun is about 400 times wider than the Moon. The Sun is also about 400 times further away. Those two numbers are not related to each other in any way that anybody has been able to find. They simply happen to be almost the same. And because they are, the Sun and the Moon appear in our sky as disks of almost exactly the same size. That is the only reason a total solar eclipse looks the way it does. The Moon covers the bright disk of the Sun almost precisely, and leaves the faint outer atmosphere visible around the edge. If the Moon were slightly smaller, we would never see that. If it were larger, it would cover it and hide it. The match is not perfect, and that is why there are two kinds of eclipse. The moon's distance varies, so sometimes its disk is a little too small to cover the sun and leaves a bright ring. That is an annular eclipse. It is also temporary in a much longer sense. The moon has not always been at this distance, and it will not stay here. We are living in the stretch of time when the two disks happen to match. The seas with no water. The dark patches you can see with your eyes have been called seas for about 400 years. Early observers with early telescopes thought that is what they were looking at, and the Latin name stuck. The Sea of Tranquility. The Sea of Rains. The Ocean of Storms. They are not seas. They are plains of solidified lava. Very large impacts early in the moon's history punched deep basins into the crust. Later, molten rock rose through the fractured floor of those basins and flooded them. It spread out flat, cooled, and set. The rock is basalt, dark and fine-grained, which is why the plains look darker than the rough, pale highlands around them. We know their age fairly precisely because astronauts brought pieces of them home, and the rock can be dated in a laboratory. Most of the lava flooding happened between about 3.5 and 3 8/10 billion years ago, which means that when you look up at the full moon, the pattern you are looking at is a record of something that stopped happening before there was anything alive on Earth more complicated than a single cell. The other side is not the same. When the first photographs of the far side came back, the surprise was not the detail, it was that the far side looks like a different place. The near side is about a third, covered by those dark lava plains. The far side has almost none. It is crowded, pale, and cratered almost everywhere. The reason appears to be thickness. Measurements of the moon's gravity field, made by two spacecraft flying in formation and watching the distance between themselves change, show that the crust on the far side is substantially thicker than the crust on the near side. On the near side, molten rock could reach the surface and flood the basins. On the far side, it mostly could not. Why the crust should be lopsided in the first place is still argued about. One explanation is that the young Earth, still glowing with heat, warmed the near side and kept it molten for longer. Another involves a second, smaller moon that collided gently and spread itself over the far side. Neither is settled. So this is one of those places where the honest answer is that we can measure the difference very well, and we still do not agree on where it came from. The dust that smells of gunpowder. The moon is covered in a layer of broken rock and dust, several meters deep in most places. It is called regolith, and it is not like dust here. Dust on Earth is rounded. Wind and water knock the corners off everything. There is no wind or water on the moon, so lunar dust keeps the shape it was broken into. Under a microscope, the grains are jagged, and some of them are tiny glass shards, made when micrometeorite impacts melted the surface for an instant. It gets into everything. It worked into the seals and joints of the Apollo suits, and it wore the outer layers visibly over a few days of use. It stuck to everything electrostatically and could not be brushed off properly. Several of the crews reported the same thing after coming back inside and opening their helmets. The dust had a smell. They described it as spent gunpowder or a fired cartridge. Nobody has fully explained it. The samples brought back to Earth do not smell of anything in particular. The best guess is that freshly broken grains, which had never met oxygen or water vapor, reacted the moment they got into the cabin air, and that the smell was that reaction happening. Why there are two tides. Most coastlines get 2 high tides a day, not 1. If tides were simply the moon pulling the sea towards it, there would be 1. The reason there are 2 is that the moon pulls on everything, not only the water. It pulls hardest on the side of the Earth nearest to it, less hard on the solid center of the Earth, and least hard on the far side. So the water on the near side is pulled towards the moon more strongly than the planet is, and it rises. And the planet is pulled away from the water on the far side more strongly than that water is, so that water is effectively left behind, and it rises too. The result is 2 bulges on opposite sides, and the Earth turning underneath them. Any given coast passes through both in a day. The Sun does the same thing, at about half the strength, and the 2 effects add or cancel. When the Sun and the Moon line up, the tides are large. When they are at right angles, the tides are small. The pattern was described mathematically in the 1680s. The underlying idea that the sea is following the moon is very much older than that. The moon is getting smaller. The moon has been cooling since it formed, and cooling things contract. Over the last several 100 million years, the moon has shrunk by more than about 50 meters across. That sounds like nothing on an object more than 3,000 kilometers wide. The interesting part is what shrinking does to a brittle crust. It cracks. Specifically, the surface breaks along thrust faults, where one slab of crust is pushed up over the slab beside it, leaving a low step across the landscape. Spacecraft photographs of the surface have found thousands of these steps, scattered all over the moon. They are also young. Some of them cut across small craters that are themselves recent, and they have not been softened by the slow rain of micrometeorites that wears everything down. That means the faulting did not stop long ago. It is still going on, which makes the moon geologically active in a modest and very slow way. Not volcanoes, and not moving continents. Just a world that is still settling, cracking as it cools, several billion years after it formed. The Quakes. Between 1969 and 1972, crews left seismometers on the surface at 5 different sites. 4 of them kept working and kept sending data until they were switched off in 1977. In those years, they recorded thousands of events. They fall into a few kinds. There are deep moonquakes, several hundred kilometers down, and these are tidal. They cluster in time with the moon's orbit, which means the Earth's pull is what sets them off. There are impacts, meteorites arriving. There is thermal cracking, the surface flexing as the 14-day night ends and the sunlight returns. And there are shallow moonquakes, which are the interesting ones. They are rare, and some of them were strong, around magnitude 5, which on Earth is enough to be alarming indoors. There is one more thing the seismometers showed, and it surprised people at the time. A moonquake on the moon does not stop the way an earthquake stops here. The signal rings on for a long time, in some cases well over an hour. The dry, fractured, uncompacted outer layers scatter the energy instead of absorbing it, so it rattles around rather than dying away. Ice in the craters. The sun never reaches. The moon's axis is almost upright with respect to its orbit around the sun. It tilts by only about 1.5 degrees. On Earth, the tilt is 23.5, and that is what gives us seasons. An upright axis has a strange consequence at the poles. The sun stays very low, skimming around the horizon, and that means the floors of deep craters near the poles are in permanent shadow. Not 14 days of night. Permanent. Some of them have not seen sunlight for billions of years. They are among the coldest places measured anywhere in the solar system, colder than the surface of Pluto, around -240 degrees Celsius. Anything that arrives there and freezes stays. Comets and hydrated meteorites have been delivering water to the moon for its entire history, and most of it is lost immediately to sunlight. What lands in those craters does not get the chance to leave. There is now good evidence for water ice in them, from several independent methods, including an impact experiment that deliberately crashed a spent rocket stage into a polar crater in 2009 and measured what came up in the plume. How much is there, and in what form, is still being worked out. The thin air. The moon is usually described as having no atmosphere. That is close enough for most purposes, and it is not quite true. It has an exosphere. This is a layer so thin that the atoms in it essentially never meet one another. On Earth, air is a gas because the molecules collide constantly. In a lunar exosphere, an atom leaves the surface, follows a long curved path, and lands again, having touched nothing on the way. The total mass of the whole thing is small. Estimates put it at something like 25 tons for the entire moon. A calm room of ordinary air on Earth contains more molecules than a cubic meter up there by a factor of about 100,000 million. It contains helium, argon, neon, and small amounts of sodium and potassium, which are convenient because they glow and can be seen from Earth. It is constantly leaking away and constantly being replaced by the solar wind, by radioactive decay in the rock, and by micrometeorites vaporizing surface material. This is worth knowing for a practical reason. Any serious activity on the surface would add more gas than the exosphere currently holds, and would change it. It is a very small thing to break. The mirrors left behind. There are working scientific instruments on the moon right now, and they need no power and no maintenance. 3 of the Apollo crews left arrays of corner reflectors on the surface. 2 more went up on Soviet rovers. A corner reflector is a simple bit of geometry. 3 mirrored surfaces at right angles, arranged so that light entering from any angle is sent straight back the way it came. An observatory on Earth fires a short laser pulse at one of the arrays and waits. The pulse spreads out on the way, covering a patch of the moon a couple of kilometers wide. It comes back spread out again. Out of a pulse containing an enormous number of photons, a single one might make the return trip and be detected. The round trip takes about 2.5 seconds. Timing it precisely gives the distance to the moon to within a few centimeters, and with modern equipment, better than that. The measurement has been repeated for over 50 years. It is one of the longest continuously running experiments in science, and it works because 5 sets of mirrors were bolted down and left in the dust, and nothing up there has disturbed them since. Where it came from. The leading explanation is that the moon was made in a collision. In the standard account, a body roughly the size of Mars struck the young Earth a glancing blow, a few tens of millions of years after the solar system formed. The impactor was destroyed. A large amount of material from both objects was thrown into orbit, and out of that ring the moon assembled itself, quickly. The idea explains several things at once. It explains why the moon has only a small iron core, if most of the iron from both bodies stayed with the Earth. It explains the Earth's tilt and the angular momentum of the system. It explains why the Moon appears to have been molten to a great depth early on. There is a serious problem with it, and it is worth stating plainly. If a large part of the Moon came from a different object, the Moon should be chemically different from the Earth. It is not. In the isotopes that have been measured carefully, lunar rock and Earth rock are almost indistinguishable. Several fixes have been proposed. A much more violent impact that mixed everything thoroughly. An impactor that happened to have formed from the same material. A different kind of collision entirely. The collision is widely accepted. The details are not settled. How long the footprints last? There is no wind on the Moon and no running water. The footprints left in 1969 are still there, sharp-edged, in the same shape they were pressed into. They are not permanent, and the reason they are not is worth understanding, because it is happening everywhere on the surface all the time. Small particles arrive constantly. Most are microscopic. Each one that lands throws up a little dust and turns over a tiny patch of ground. Averaged across the whole surface and a very long time, this slowly stirs and smooths everything. The process is called gardening. It is extremely slow. Estimates for how long a boot print stays recognizable run to millions of years, and the figures vary depending on the assumptions about how much material is arriving. So the honest statement is this: the footprints will outlast almost everything built on Earth. They will outlast most human structures by a factor of thousands, and they will still be gone, eventually, worn away by a rain so faint that it takes 1,000,000 years to sweep a floor. That is 14 things about one object. It is worth remembering how close it is relative to everything else we talk about. The Moon is about a light second and a bit away. Everything else in these episodes is minutes, hours, years, or thousands of years distant. The Moon is the one place near enough that people have gone there and come back within a fortnight. It is also the only object in the sky whose surface you can study with your own eyes. The dark plains are visible without any equipment at all. A pair of binoculars held steady will show you craters. If you are still awake, it is probably up there somewhere right now, keeping the same face towards you that it has kept towards everyone who has ever looked at it. Sleep well.